The spacecraft falls toward the star like a seed drawn into a furnace. Its heat shield faces the glare, a dark plate absorbing a brightness that feels more like pressure than light. The sun fills every horizon. Its surface boils, shifts, and shimmers in currents that look alive. The probe does not flinch, but the world around it changes with every kilometer of descent. The luminous shell that should grow cooler with distance from the surface instead rises in temperature until it becomes a crown of fire, hotter than the star beneath it. The corona blazes at millions of degrees, while the photosphere rests thousands below that mark. This is not how heat should behave. This is not how stars should behave. If energy moves outward, why does the outer skin scorch more fiercely than the place where fusion begins? Its edge should fade into space, yet it burns with a force that does not fit any simple rule. The spacecraft dives deeper. Radiation thickens into a haze of charged particles, each moving with a speed that would shred a human body in an instant. Currents of plasma twist as though stirred by invisible hands. Sudden bursts of energy push outward, then curl back in sharp arcs. The solar wind should stream smoothly, yet here it changes direction without warning. A river that turns back on itself, a current that rebels against the shape of the star. The probe flies through these reversals, as though navigating a maze without walls. Each switch feels like a small jolt in the readings, as if the magnetic field is snapping into a new form faster than thought. Why would a star send out streams of particles only to whip them backward? What force inside this furnace is powerful enough to pull at its own light? The corona stretches above the sun like a veil of fire. From a distance it appears serene, but from within it behaves like a restless sea. Loops of magnetic energy lift hot plasma high into the air. Some loops break and reform, releasing pulses of heat that surge outward like invisible waves. The spacecraft records each one as a spike of force. It drifts through storms made of particles rather than rain. The soundless space around it is full of motion anyway, a place where disturbances ripple with no air to carry them. If the sun were quiet, the corona would be a thin blur. Instead, it is a theater of eruptions, shocks, and reversals. The star is not a calm sphere of fire. It is a machine that tears at its own boundaries. The deeper the probe flies, the more contradictory the environment becomes. Light glows evenly, but particles crash in tangled paths. Fields shift in patterns that no telescope on Earth can trace from afar. Heat rises upward where it should fall. Winds bend where they should flow straight. Energy lifts from the star in sudden bursts that defy the ordinary rules of physics. Think of holding your hand near a flame only to discover that the hottest spot is in the air above, not in the fire. This is the nature of the corona. A place where intuition fails. A place where the sun breaks its own logic. Beneath the surface of this chaos is a structure that the human eye cannot see. The magnetic field stretches outward in spirals and arcs. Some lines twist into knots. Some snap and reconnect, releasing packets of energy that race toward the probe. Each event lasts only a moment, but together they form a constant storm. The spacecraft senses every shift. It adjusts its position with small corrections, staying aligned so the heat shield catches the worst of the radiation. There is no silence here. There is only the constant push of particles, the subtle vibration of force, the ceaseless glow of a star that does not stop shaping the space around it. The closer the probe gets, the more the sun reveals itself as a place of contradictions. Heat flows in the wrong direction, winds move with moods, fields carve patterns that last seconds before folding into new ones. Inside this disorder may lie the answer to how the solar wind gains its speed. Some waves of energy seem to give particles the extra push they need to escape the star. Others appear to redirect them into loops that cross and recross the same path. Could these strange reversals be the engine that launches matter across the solar system? Could the corona be a gateway where heat and force collide to create the winds that shape every world we know? The light intensifies as the spacecraft reaches its closest approach. The entire universe appears to shrink to a single star and the narrow band of darkness around it. Every sensor reads extremes. Temperatures soar, fields spike, particles rush past at speeds that would tear metal if not for careful engineering. Yet the probe continues. It dives again and again, orbit after orbit, peeling back the layers of the sun with each pass. Somewhere within these passes is an answer, but the star does not release it easily. The corona behaves like a veil that hides more than it shows. It flickers, shifts, and burns with a fury that feels ancient and unconstrained. What does it mean that the most familiar star can still surprise us? What does it mean that the place we thought we understood is far stranger than predicted? We once viewed the sun as a constant, a reliable engine that warms our world. Now we see its outer layers behave like a wild frontier. If this is how our own star behaves, what happens in the atmospheres of stars more massive or more unstable? How many other coronas behave like this? How many break their boundaries in ways we have never imagined? The spacecraft drifts through another burst of charged particles. It is mapping the breath of the sun from the inside out. Each turn reveals new motions, new signals. They appear like fingerprints rather than chaos. Patterns emerge, then dissolve, then hint at deeper shapes. The probe is close enough to feel the currents that start the solar wind, close enough to sense how the sun pushes and pulls the space around it, close enough to glimpse the inner tension of a star that refuses to settle. This proximity is not simply about distance. It is about perspective. Standing on Earth, we see the sun as a single disk of light, flying through the corona. The spacecraft sees it as a layered world where force and heat collide. The boundary between order and disorder blurs. The sun is not a steady glow. It is an ocean of fire shaped by magnetic tides. If the nearest star contains this much complexity, what mysteries lie in the spaces beyond? Where does the influence of the sun begin to wane? Where does another realm begin? The star grows behind the probe as it completes its pass, leaving trails of signals to decode. These signals form a path toward the next frontier, where the solar wind departs the sun entirely and begins its long flight to the edge of the solar system. The mysteries of the solar wind will lead us outward, away from the furnace, toward the region where magnetic chaos becomes a planetary force. As this descent closes, the path forward becomes clear. What begins at the sun will guide us toward the strange behavior of the winds that fill all space between the planets. The spacecraft drifts inward along a trajectory that feels less like an orbit and more like surrender. Its heat shield faces the star, a blackened plate absorbing a brilliance that presses against every surface like a physical weight. The sun grows until it fills the entire sky, an expanse of shifting light that looks calm from afar, yet rages in ways no eye can truly see. Beneath the apparent glow lies a realm of collisions, fields, eruptions, and silent violence. The probe enters this realm with deliberate purpose. It is here to measure the breath of the star from the inside. It is here to step into a furnace that refuses to obey its own rules. The closer it moves, the more fiercely the world around it behaves. The photosphere shimmers at one temperature, but the corona above it rises to far hotter levels, millions of degrees in a layer that should be cool. Heat should fade outward, yet here it surges up. It is as though the star has turned itself inside out, lifting energy to the boundary rather than keeping it near the surface. This inversion is one of the oldest riddles in solar science. Why does the edge burn hotter than the surface below? What lifts that energy? How does a star manage to contradict a rule that seems so simple? When the probe crosses into the corona, the contradiction is no longer an abstract puzzle. It becomes the airless weather that strikes the hull. Particles race outward from the sun in streams that twist like living currents. Protons and electrons surge through the corona at speeds that defy instinct. These charged particles move along magnetic paths that knot and bend. Some paths stretch into space. Others curl back toward the star. The wind is not a steady flow. It is a storm full of sharp changes. At intervals that last less than a heartbeat, the magnetic field flips briefly, space bends, the direction of the wind reverses. The probe detects these reversals as sudden jolts. They are called switchbacks. They are small, yet powerful clues that something deep inside the sun is shaping the flow of energy in a way Earth-based telescopes cannot see. The probe moves through one switchback after another. Each one marks a place where the magnetic field folds. If we could see these fields, they would appear like luminous roots growing outward. Some roots twist into spirals. Others break in bursts of lightless energy. The probe senses these events through rapid changes in particle direction and density. Observing them from within feels like tracing the heartbeat of the star. Every pulse carries heat. Every reversal carries momentum. Every surge hints at a mechanism that turns magnetic tension into motion, motion into heat, heat into the violent glow of the corona. The light surrounding the spacecraft is steady, but the invisible forces are chaotic. Magnetic lines create invisible walls that collide and snap. These events send packets of energy outward. Some packets accelerate the solar wind. Others distort it. All of them remind us that the sun is not simply a sphere of fusion. It is also a realm of shifting fields that rise and collapse as constantly as waves in an unseen ocean. The spacecraft moves through these fields like a diver moving through tidal currents. What seems calm from above becomes turbulence from within. Closer still, new details emerge. The corona is not a smooth halo of heat. It is a structure full of pockets, ridges, and filaments. These forms pulse with high energy waves that roll across the star like tremors. Some waves carry enough power to push matter outward with great force. These waves might be the culprits behind the extreme heating of the corona. They may rise from the tangled base of the sun's magnetic roots. They may burst upward from deeper layers where convection and magnetism collide. The probe cannot see those deeper regions, but it can feel the echoes of those collisions through the violence in the surrounding plasma. Throughout this journey, the spacecraft maintains alignment with its heat shield. Its sensors run as efficiently as they can in such an intense environment. Automated systems guide the craft without waiting for contact with Earth. Even the faintest delay would be too slow. The sun does not grant enough time for hesitation. Radiative storms form without warning. Charged particles can strike faster than a signal can travel across the inner solar system. The probe survives by reacting instantly. It adjusts its position to keep the shield pointed toward the star. It continuously measures the incoming wind. It protects itself by understanding the environment before the environment can destroy it. The deeper it dives, the more the corona reshapes the idea of what a star is. From Earth, the sun looks constant. From orbit, it becomes unstable. From within the corona, it becomes a storm of magnetic forces. The probe encounters regions where the particle density changes sharply, as though crossing weather fronts in an atmosphere of plasma. It moves from quieter pockets into violent ridges. Each ridge is a sign that magnetic fields have recently reconnected. When field lines snap and reform, energy that was stored in tension is released in bursts. These bursts may be the small flashes known as nanoflares. A single nanoflare is too small to see from Earth, but millions of them may provide the heat needed to raise the corona to its extreme temperature. The probe does not see nanoflares directly. It sees the consequences in the motion around it. Somewhere within these layers, the solar wind forms its true shape. Particles gain speed gradually, gathering energy from waves and shocks before escaping the gravity of the sun. The probe is close enough to sense the acceleration process. This region is the birthplace of the wind that fills the solar system. Beyond this zone, the wind becomes a river of particles streaming toward planets, moons, and distant boundaries. Here, at the source, the wind is a series of gusts, pushes, stalls, and reversals. Understanding these early motions may be the key to predicting solar storms that can disrupt satellites, power systems, and astronauts. Each reading from the probe becomes part of a larger map of solar behavior, a map that may one day help shield our technology and our future missions. As the craft continues its plunge, the corona begins to reveal new patterns. Heat and motion do not distribute evenly. They form channels. Some channels seem to rise from deeper layers, carrying plasma along paths carved by magnetic fields. Others branch outward. The probe crosses one such channel. Here, particle energy spikes, then declines, then rises again, as if governed by a pulse. Could this be linked to oscillations beneath the surface? Could it be a wave driven by the sun itself? Or is it simply the local effect of twisted field lines snapping back into alignment? Around the probe, the corona glows, not in visible wavelengths, but in ultraviolet and other bands the spacecraft can detect. These emissions reveal regions of intense heat. They mark the presence of active magnetic loops and rising plasma. The glow shifts constantly, like the shimmer of northern lights magnified to a scale beyond imagination. Moving through this glow, the probe becomes the first emissary of a species trying to understand the furnace that made life possible. Here, in the inner corona, the star's personality becomes clear. It is not steady. It is restless. The signals drifting into the spacecraft do not form a smooth pattern. They shape a language of fluctuations. A rise, a dip, a sudden jolt of wind, a reversal of direction, a surge of temperature. Each shift is a word. Each shock is a sentence. The spacecraft reads them one by one, building a story from fragments of force and fire. Why does heat rise into the corona? Why do particles loop back toward their source? Why does the solar wind begin here with such disorder? What secret mechanism at the edge of the sun can give rise to storms powerful enough to disturb planets? These questions hang in the airless space like silent companions. The probe cannot answer them alone. It can only collect the clues. As the spacecraft completes its closest approach for this pass, the view expands slightly. The star is still overwhelming, but the corona now reveals a sense of structure, a sense of depth. The probe drifts through the last bursts of charged particles. It exits the most violent region and enters a zone of relative calm. Here, the wind becomes steadier, the fields feel smoother, the chaos begins to settle. This calm will not last, but it is enough to glimpse the next frontier. The wind that begins here does not remain gentle for long. It grows into the force that shapes entire planetary environments. It influences magnetospheres, atmospheres, and radiation belts. It stretches outward across billions of kilometers. It becomes the medium through which the planets drift and the shield that defines the boundary of the solar system. The path ahead points toward these winds and their strange behavior, a journey that will lead from the heart of the corona to the strange turns of the solar wind itself. Far from the surface of the sun, the spacecraft rises into a realm where the furnace gives way to flow. The glow of the corona softens behind it, but the influence of the star does not fade. Instead, it stretches outward in streams of charged particles that fill the space between worlds. This is the solar wind, the river of plasma that bathes every planet, moon, and rock in the system. It is easy to imagine it as a smooth, steady outflow, a gentle breath that expands into the dark. The instruments on the spacecraft tell a very different story. The river is jagged. It twists. It folds back on itself. It behaves like a flow that has forgotten which way is downstream. The first clue to this disorder appears in the data as sharp kinks. The magnetic field the craft is flying through suddenly flips direction, then flips back again. The solar wind at that moment does not simply stream away from the sun, it momentarily points back toward it. The spacecraft is still moving outward, but the local wind seems to turn around and rush past as if retreating. These brief reversals are the switchbacks. They look like sudden hooks in the magnetic field, small but frequent, scattered through the flow like knots in a rope. Why should a wind born at the sun suddenly behave as if it is falling back toward its source? Why does a river of plasma act as though it is running uphill? From a distance, the solar wind smears into an average. Telescopes see brightness, not the fine structure of the flow. Models once treated the wind as a smooth stream with minor turbulence. Inside that stream, the spacecraft experiences something much less polite. The wind changes speed in steps, not in gentle slopes. Patches of fast flow slam into slower regions, creating boundaries where particle densities jump. Temperatures vary from pocket to pocket. To move through this medium is to move through a broken mirror. Every assumption about direction, speed, and structure is reflected back in pieces. Magnetic measurements reveal that the switchbacks are not random hiccups. They appear more often in some regions than others. They cluster near certain latitudes and longitudes. In some passes, the field bends so sharply that the local direction of the wind points almost completely back at the star. In others, only small angles are seen. The overall effect is a jagged pattern rather than a smooth spiral. For decades, the expected shape of the solar magnetic field in the outer system was drawn as an elegant curve, like water spiraling from a spinning sprinkler. The spacecraft inside the inner heliosphere finds something more like a tangled spray of jets. How can a field that sketches a graceful spiral far away be made of so many crooked segments close in? The contradiction deepens when the timing of the switchbacks is examined. Some occur in rapid bursts, clustered so tightly that the data looks almost like static. Others are separated by calmer intervals. They often appear linked to regions where the solar wind is faster. That suggests they might arise from deeper roots, perhaps tied to the open magnetic field lines that connect down into the sun's lower atmosphere. If the solar wind is born on those open lines, any disturbance at the base could ripple outward as bends in the field. The spacecraft might be sensing the fingerprints of processes happening far below its path. One idea paints the switchbacks as the visible scars of waves rising from the sun's surface. These waves travel along magnetic structures like ripples along a rope that is shaken at one end. As they move outward, they can steepen into shocks, compress the plasma, and fold the field. In this view, the river that turns back is not confused. It is responding to the push and pull of waves that carry energy out of the star. These waves may be one of the missing pieces in the mystery of how the solar wind gains its speed. If they give particles extra momentum, they can help them escape the sun's gravity. If they bend the field, they can create the broken mirror readings that confuse simple models. Another idea sees the switchbacks as marks of reconnection. Magnetic fields that point in opposite directions can be forced together by the motion of plasma. When they meet, they can break and rejoin in new combinations, releasing stored energy in the process. These reconnection events can launch jets of plasma and fold the field into looped shapes. The spacecraft might be threading through the aftermath of countless small reconnection bursts. Each burst changes the local structure of the field. Each change is recorded as a flip, a kink, a brief moment when the wind rushes past in the wrong direction. Whatever their origin, the switchbacks are more than a curiosity. They influence how energy and momentum are distributed through the heliosphere. Regions with strong switchback activity can scatter particles more efficiently. They can alter how cosmic rays from outside the solar system propagate inward. If you picture the solar system as a vast region of weather made of charged particles, then switchbacks are the fronts and eddies that shape that weather. They are not just oddities in the data, they are structures that define how risky space can be for technology and for life. Consider a simple satellite around Earth. It orbits in a region where the planet's magnetic field pushes back against the solar wind. That field is not fixed. It flexes as the wind changes. When solar wind structures, including switchback-rich streams, strike the magnetosphere, they can trigger magnetic storms. These storms in turn can induce currents in power grids, disturb radio communications, and increase radiation levels for spacecraft. A kink in the wind near the sun can ripple outward and eventually translate into flickering lights and disrupted navigation systems on a planet far away. This is one reason why understanding the broken mirror pattern of the solar wind matters so deeply. Beyond the immediate technological concern lies a broader story. The solar wind carves out the heliosphere, the bubble in which all the planets move. That bubble is not a perfect sphere. It is warped by the surrounding interstellar medium and by the wind's own inner structure. Switchbacks may help determine how energy is distributed across that bubble. If they guide waves or alter the paths of particles, they can shape the thickness of the heliosphere in different directions. That thickness, in turn, affects how well the sun protects the planets from the harsher radiation of the galaxy. To gain a clearer picture, scientists compare measurements from close in with those taken farther away. Spacecraft near the sun see the wind full of sharp reversals. Probes near Earth see a more blended flow, but still with hints of distinct streams. Farther out, toward the outer planets, the solar wind has merged into broad flows and large-scale structures. Coronal mass ejections, the vast eruptions of plasma from the sun, ride on top of this background wind like storms on a moving ocean. The switchbacks near the sun may be part of how that background is stirred. They may be among the smallest visible scales in a cascade of structure that stretches all the way out to the edge of the heliosphere. If that is true, then the river that turns back near the sun is part of the same system that shapes the environment at Jupiter and beyond. In this view, the broken mirror is not simply broken. It is a complex lens. It distorts, but it also reveals. By flying through the switchbacks, the spacecraft is sampling the early form of the wind that will later collide with planetary magnetic fields and atmospheres. The detailed structure near the sun may explain why some regions around planets are bombarded more heavily than others, why some orbits are harsher for spacecraft, and why auroras bloom differently in different places. To make sense of this, the mission does not rely on one pass alone. It returns to the inner heliosphere again and again, each time at a slightly different angle, each time catching the wind in a different mood. The data sets pile up. Patterns that seemed like noise begin to show repetition. Some switchback-rich streams appear tied to long-lived regions on the sun. Others emerge from more transient sources. A picture begins to form of a star whose output is patterned but not simple, ordered but not smooth. The river is wild, but it is not random. At the same time, the spacecraft has allies farther out. Other probes carry instruments designed to read the solar wind at distances near Earth and beyond. By comparing these readings, it becomes possible to track how a patch of wind evolves as it flies away from the sun. Does a stream full of switchbacks smooth out with distance? Does its jagged field remain fractured? Does its speed change? Does its density spread or clump? If the answers to those questions can be mapped, then the entire corridor from the corona to the outer planets can be understood as one continuous, transforming flow. In everyday language, the solar wind is the medium in which our entire planetary system is immersed. It is the background weather of space. Measuring its structure near the sun is like putting sensors in the mountains where a great river begins. The twists and falls there tell you how the water will move through valleys, plains, and deltas far downstream. When you know the source, you begin to understand the path. The deeper implication stretches beyond our own star. Every star with a magnetic field likely produces its own version of a stellar wind. These winds carve out their own bubbles in the interstellar medium. They shape the environments of exoplanets and control how much high-energy radiation reaches their surfaces. If the sun's wind is this complex, then the winds of other stars may be at least as intricate. The switchbacks we see here could be a local example of a universal behavior. They may be hints that stellar environments everywhere are built from the same kind of broken mirrors and turning rivers. This matters when we think about habitability. A planet can sit in the right orbit for liquid water, but if its parent star floods it with violent, poorly filtered particles, the surface may remain hostile. The fine structure of a stellar wind can either spare a world or batter it. Understanding how the sun's wind forms, changes, and interacts with magnetic fields helps us guess how other stars treat their planets. It becomes part of the quiet background that decides where life can emerge and endure. As the spacecraft finishes another sweep through the inner solar wind, it leaves behind a trail of questions written in charged particles and magnetic angles. The data now show a river that turns back on itself, a flow full of kinks that do not fit old pictures. They also show patterns that reach outward, hinting at connections to much larger structures. The broken mirror is beginning to show not just cracks, but reflections of something beyond. Ahead lies the realm where this wind collides with giants. The same flow that twists near the sun will soon crash into the deep magnetic wells of the outer planets, and in that collision, the true shape of both wind and planet will be revealed. Jupiter appears first as a swollen disk of cloud and storm, but the closer the spacecraft comes, the more it becomes clear that the planet is only the center of a much larger presence. Long before the ship reaches the cloud tops, it enters an invisible structure that dwarfs the giant itself. This is the magnetosphere, a bubble of charged particles and magnetic field that stretches farther than the sun appears wide in the sky. The probe crosses a threshold, and the instruments come alive. The numbers jump. The background hum of particles grows into a roar. It is like walking through a doorway and realizing that the building is not a room, but a vast maze. The first clue that this maze is different from anything near Earth lies in the radiation. Intuition says that farther from the sun should mean calmer conditions, softer light, quieter space. Yet here, 500 million miles from the furnace, the radiation levels climb so high that unshielded electronics would fail in moments. Electrons spiral along magnetic lines at nearly the speed of light. Protons strike with enough energy to break molecular bonds. Jupiter is not a distant calm world. It is a storm anchor. Why is space this harsh so far from the sun? Why is the environment of a cold giant more deadly than many regions much closer into Voyager? The spacecraft passes through belts of trapped particles that wrap around Jupiter like invisible rings. These belts are thicker and more energetic than those near Earth. They pulse and shift as the planet spins and as the solar wind pushes at the outer boundary. Within them, 4 large moons trace their orbits. Each world moves inside the field, not outside it. Io, Europa, Ganymede, and Callisto are not simply circling a planet, they are embedded in a magnetic labyrinth. Io offers the next clue. Its surface is mottled yellow and black, scarred by calderas and lava fields. It is the most volcanically active body in the solar system, a world that erupts even though it sits far beyond the traditional warmth of the sun. Great plumes of sulfurous gas rise hundreds of kilometers above the surface, then fall and freeze in bright patches. How can a world this far from solar heat be hot enough inside to melt rock? How does a moon without its own strong magnetic field carve such a deep mark into Jupiter's environment? The answer begins with tides. Io does not orbit in a perfect circle. It is tugged constantly by Jupiter on one side and by the other moons on the other. This never-ending flexing kneads the interior, turning gravitational energy into heat. Rock bends and cracks. Magma rises. Volcanoes erupt, again and again. Each eruption feeds a torus of gas and ions around Jupiter, centered on Io's orbit. In that torus, particles stripped from the moon become fuel for the magnetosphere. The maze gains new walls from a moon that is slowly transformed by the stress of its path. The spacecraft senses the presence of this torus as a rise in ions of sulfur and oxygen. It flies through a faint, invisible donut-shaped region that glows only in certain wavelengths. Io's contribution does not end at chemistry. As the moon moves through Jupiter's magnetic field, it acts like a conductor cutting through lines of force. Electric currents flow along the field lines between Io and the planet. These currents carry power that would dwarf our global energy use. They strike Jupiter's upper atmosphere near the magnetic poles, lighting up bright spots in the auroras. The footprints of Io on the Jovian sky are a reminder that moons can write directly onto the magnetic face of their planet. Ganymede presents a different sort of puzzle. While Io burns, Ganymede bears ice and rock. Its surface is older, carved by craters and grooves. quieter at first glance. Yet it hides something extraordinary. Ganymede hosts its own internal magnetic field, generated by motion in a liquid metallic core. This field carves a small bubble inside Jupiter's larger magnetosphere. Inside that bubble, charged particles move differently. It is as if a city inside the labyrinth has built its own sky. The spacecraft, passing near Ganymede, can detect the boundaries of this nested field, where Jupiter's dominance weakens and the smaller moon's influence grows. Europa, smoother and more subdued, brings another layer to the maze. Its surface is a cracked shell of ice, crisscrossed with dark lines and ridges. Measurements of its magnetic response hint at a salty ocean beneath that shell, a global sea kept liquid by gentle tides. When Jupiter's field sweeps across Europa, it induces currents in that ocean. Those currents in turn create a secondary field, a subtle echo that the spacecraft can measure. The labyrinth of fields becomes deeper still, running from planet to moon to hidden water. A world locked in ice becomes part of the electromagnetic story, even without eruptions or visible storms. Think of it like this. Jupiter is not only a planet, it is a generator turning rotation and magnetic structure into energy that floods the space around it. The moons are not only satellites, they are moving conductors, resonant spheres, and heat engines that shape and are shaped by that generator. The entire system behaves like a machine made of many parts, each interacting through gravity, motion, and magnetism. The contradiction that emerges is clear. These moons exist in a region that should be dark and cold, yet inside this maze they are anything but quiet. Eovent's lava. Europa likely hides a warm ocean. Ganymede maintains its own magnetosphere. Radiation storms wrap everything in high-energy particles. Distance from the sun does not equal safety. It does not guarantee stillness. Instead, the interplay of gravity and fields creates pockets of energy and activity that rival anything near the inner planets. The spacecraft circles along a path that slices through this complexity. Sometimes it dives through the dense parts of the radiation belts, where particles hail against it like a constant storm. Sometimes it skims the magnetic equator, tracing the stretched tail of the magnetosphere as it is pulled back by the solar wind. Each pass reveals how much structure lies in what was once drawn as a simple bubble. There are lobes, cusps, sheets, and layers. There are regions where flux tubes connect planet and moon, creating direct routes for particles to travel. There are zones where plasma from Io is trapped and accelerated until it becomes one of the major sources of radiation in the system. Why does this matter beyond the beauty of the physics? Why is it more than a local curiosity? The answer lies in habitability. Radiation that intense is a hazard for both life and machines. Any future mission that hopes to land on Europa or orbit Ganymede for extended periods must learn to navigate this labyrinth. Spacecraft need orbits that minimize time in the most dangerous belts. Landers must be sheltered against storms that can arise with little warning. Understanding the shape of the fields and the sources of the most intense flux is not optional. It is the difference between a mission that endures and one that fails. At the same time, the very processes that make this environment harsh may create conditions where life could exist beneath the ice. Tidal heating keeps Europa's ocean liquid. Currents induced by the magnetic field may stir that ocean, bringing chemicals and energy together. On Earth, deep oceans around hydrothermal vents host dense ecosystems without sunlight. They rely on chemistry, not on starlight. If Europa or similar moons host vents at the seafloor, heated by tidal flexing and influenced by the exchange of materials with the surface, they may harbor pockets of chemistry that edge toward biology. The maze of moons and fields may be a cradle as well as a barrier. Each measurement the spacecraft makes helps build a model of how magnetospheres and moons co-evolve. This model does not apply only here. Giant planets around other stars are common. Many are closer to their stars than Jupiter is to the Sun, making their fields and winds even more intense. If they host large moons, those moons may experience heating and magnetic interactions on a scale even greater than we see here. Some exomoons could be roasted, stripped, or sterilized. Others could gain hidden oceans and internal heat that allow complexity to arise far from the glare of their stars. Jupiter's labyrinth becomes a key for understanding countless unseen systems. Questions multiply as the spacecraft flies on. How stable are the radiation belts over long spans of time? Do the footprints of Io and the other moons change as volcanic activity rises and falls? Does Ganymede's small magnetosphere shield its surface significantly, or does the broader Jovian field always dominate? How deep are the induced currents in Europa's ocean? And how much energy do they deliver? What happens when a strong burst of solar wind compresses the magnetosphere and drives its inner regions tighter around the moons? From its vantage within the maze, the probe can only answer some of these questions. It samples one orbit at a time, one alignment of moons and fields, one moment in a changing pattern. Yet each cross-section is a piece of a larger shape. Over time, a picture emerges of a system in constant negotiation. Gravity pulls one way, magnetic tension pulls another. The moons tug on each other. Plasma from Io drifts outward and inward. The solar wind pushes at the boundary. Nothing here is static. Everything is shaped by the interplay of motions and invisible lines. At the heart of this labyrinth, Jupiter rotates. Its rapid spin helps generate the magnetic field in its deep interior, likely in a layer of liquid metallic hydrogen. That dynamo sends out lines of force that trap particles and define the shape of the magnetosphere. The link between deep interior and distant boundary is unbroken, even if it is complex. What happens in the hidden core is written in the auroras at the poles. What happens at the poles is written in the currents that run down to Io. What happens at Io feeds plasma into the belts that bombard other moons. It is one continuous story. The spacecraft, watching the auroras flicker in ultraviolet and infrared light, sees that story drawn directly onto the planet. Bright spots mark the footprints of the Galilean moons. Curtains of light trace the arrival of fast plasma streams from the outer magnetosphere. When the solar wind presses hard, the auroral ovals brighten and widen. From these signals, scientists can read the balance of forces at work. Each glow is a sign, each dimming, each flare, a change in the flow. As the mission continues, the data from Jupiter find their place alongside the readings from the Sun, the chaotic magnetism near the corona, the broken mirror of the solar wind, and the labyrinth of Jupiter's fields are all parts of a single chain. Energy rises from the star, rides outward on the wind, and crashes into this giant. The response of the Jovian system sends ripples back, altering the texture of that wind farther out. The maze is not isolated. It is a node in the larger network of the heliosphere. The path forward from here does not lead back toward the Sun. It leads outward, toward another giant world where rings, rather than moons, reveal how delicate and unstable a planetary environment can be when ice and rock orbit at the razor edge between structure and collapse. Saturn rises out of the dark like a lantern wrapped in glass threads. From a distance, the planet and its rings look perfectly composed, a simple icon of order in the outer system. The globe glows with bands of muted gold and cream. The rings float around it in thin, bright arcs that look flat, smooth, and timeless. The image invites a comforting idea. Here, at least, the universe has drawn one clean shape. When the spacecraft approaches, that idea begins to break apart. The rings are not a single object. They are billions of pieces in constant motion, and their very existence raises a question the eye cannot answer. Are we looking at stability, or at a structure in the middle of falling apart? As the probe slips into Saturn's plane, the rings change from a flat curve to an environment. What looked like a solid band becomes a sheet of icy particles stretching from the edge of the planet out for tens of thousands of kilometers. The brightest main rings are only a few tens of meters thick in many places, but they span a width that could contain worlds. Particles the size of dust grains share orbits with chunks as large as houses. They collide, stick, shatter, and scatter sunlight like a sea of broken mirrors. How can something so thin have such power over the way we imagine the planet? How can something built of fragments appear so complete? The first contradiction appears in their age. For years, it was comfortable to imagine the rings as ancient, perhaps as old as Saturn itself, a relic from the formation of the solar system. But the data do not sit quietly with that story. The rings are bright, too bright. Dark dust from comets and interplanetary debris should have stained them over billions of years. Instead, much of the ice still gleams. Measurements of their mass and how fast that mass seems to be draining inward suggest that the rings might be young, perhaps only a few 100 million years old. If that is true, then we are witnessing a temporary feature, not a permanent crown. What kind of system produces a structure this vast, then lets it decay on a timescale that fits inside the history of complex life on Earth? Closer inspection deepens the puzzle. The spacecraft flies above the rings and looks down, using instruments that can sense fine variations in density and height. The rings are not smooth sheets. They are full of waves, ripples, and sharp edges. Gravitational pulls from Saturn's many moons carve patterns into them. Some moons orbit just outside the main rings, their gravity corralling particles into narrow bands. These are the shepherd moons, guiding and confining ring material along particular paths. Other moons, farther out, tug from a distance. Their orbital resonances create spiral density waves, where ring particles bunch up into regularly spaced ripples. The rings respond to these pulls like a fluid that can hold a shape for a time, then break it again. The A-ring, one of the major components, hosts scars that look like small gaps and streaks. Some of these features are caused by unseen clumps moving through the ring, stirring material as they pass. They leave trails called propeller structures, hints that moonlets only a kilometer or so across can open small pathways but never quite clear them. These moonlets are too small to be stable in the long term. Collisions will grind them down, and their orbits can shift under the constant influence of Saturn and the larger moons. The rings appear to be constantly building and erasing these small bodies. Creation and destruction happen side by side in an endless cycle. In everyday language, the rings are a balancing act between being a moon and being dust. Individual particles follow orbits set by gravity, but they also collide so often that their behavior begins to resemble that of a fluid. Too much mass in one place, and a moon can begin to form. Too much agitation, and that forming body is broken apart. Return to the ring. The system hovers near the threshold where clumps grow just enough to begin to coalesce, only to be stripped away by the next gravitational nudge or collision. Saturn's rings sit on the razor edge between making something and erasing it. What does this say about how planets and moons form elsewhere? The rings may be a small-scale analog of the disks that once surrounded young stars. In those protoplanetary disks, dust and ice grains collided, stuck together, and gradually built planetesimals and worlds. But those disks were not quiet, either. They too were stirred by gravity, by spirals, by turbulence, by the pull of growing planets. Looking at Saturn's rings is like looking at a fossil, not of the early solar system directly, but of its style of construction. The waves and gaps show how structure can arise from chaos. The propellers and moonlets show how tentative growth can be, how easily a nascent body can be shredded before it becomes something new. One of the most striking discoveries comes from gravity measurements. When the spacecraft uses its radio signals to track its motion near the rings, subtle changes reveal how much material is pulling on it. Those measurements suggest that the rings are lighter than many earlier models assumed. A lighter ring system runs out faster. It cannot hold its form for billions of years without change. Micrometeoroids steadily erode the ice, and the bombardment sends a fine rain down into Saturn's upper atmosphere. There, the material becomes part of the planet, marking the slow death of the rings as they fall. The grand structure we see now may be a brief show in the long life of the planet. Why should that bother us? Why should it matter that the rings might be temporary? It matters because it changes how we think about other systems. If Saturn's rings are young, They may have formed from the breakup of a moon that wandered too close, or from the disruption of an icy body captured and torn apart by tides. That would mean that ring systems of this scale might appear and disappear multiple times over the age of a planetary system. Looking outward to distant exoplanets, we might be catching some giants in their ring-rich phase, while others have already lost theirs. Rings become a chapter in a long narrative, not a permanent trait. The instability is not only temporal, it is also spatial. Edges that look sharp are constantly under attack. Resonances with moons can sharpen a boundary, but impacts and orbital diffusion blur it. Vertical warps tilt portions of the rings slightly above and below the main plane, creating corrugations that the spacecraft can trace. These warps are like memories of past disturbances, perhaps cometary impacts or shifts in Saturn's own interior that altered the timing of its gravity field. The rings are a seismograph, recording events that shook the system over millions of years. From a human scale, it is hard to imagine such thin structures being so complex. You could drive a car across the vertical thickness of many ring regions in seconds, yet their horizontal extent would take you longer than a lifetime at highway speed. The particles that make them up can be small enough to hold in your hand, yet together, they manipulate light, gravity, and chemistry on a planetary scale. A single ring particle is a grain of ice. Billions of them together are an environment that can trap signals, focus waves, and alter the rotation of the planet itself through subtle exchanges of angular momentum. Rings also influence the moons that orbit near or within them. Material slowly drifts outward and inward, and some of it strikes nearby moons, altering their surfaces and perhaps feeding thin atmospheres or tenuous dust envelopes. Some small moons might even be partly grown from ring material that has clumped and adhered around a rocky core. Others may be slowly eroding back into the ring. This two-way exchange blurs the line between moon and ring, object and environment. The spacecraft's instruments record not only the static picture of the rings, but their time-dependent behavior. Brightness variations reveal how quickly waves travel through the particle disk. These waves move at speeds that depend on the local density and the mass of Saturn. In some cases, the patterns coincide with oscillations inside Saturn itself. The planet's interior vibrates like a bell, and those vibrations subtly change its gravity, which then imprints waves into the rings. Reading those patterns is like listening to the ring system recite the music of the planet's interior. That connection turns the rings into a tool for probing what lies beneath Saturn's clouds. Why does this connection matter? Because it reminds us that what we see as separate is often linked. The rings, the moons, the deep interior, and even the solar wind interact in ways that reveal hidden information. A planet's gravity field can be read from the motion of ring particles. A moon's mass and internal structure can be inferred from the gaps and edges it creates. The external motions of ice grains can tell us about unseen motions of fluid hydrogen thousands of kilometers below. There is a larger, more philosophical consequence as well. The rings are beautiful, but that beauty is not a static sculpture. It is the visible face of ongoing processes that will eventually erase the very thing we admire. Watching them closely forces us to confront the idea that stability in the cosmos often means balance between opposing actions, not the absence of change. Rings persist because destruction and formation roughly cancel each other over certain timescales. When that balance shifts, the system moves on. As the spacecraft pulls away on its trajectory, the rings thin once more to a fine curve against the dark. From this distance, the waves, gaps, and moonlit scars disappear into a single, clean shape. It is tempting to let the mind smooth everything over, to remember only the simplicity. Yet the data stored within the craft hold the real story, one of constant motion and quiet decay. The ringed giant returns to being a symbol, but we now know the symbol rests on a restless foundation. Ahead lies a region where that restlessness takes a different form. Beyond Saturn, the solar system cools further, and worlds of ice and rock circle the sun in paths that seem slow and uneventful. Yet their surfaces and interiors move in ways that defy their distance from the light. Beyond Saturn, the light thins. The sun shrinks to a sharp point that could be covered with a fingertip held at arm's length. The warmth that once dominated everything becomes a pale influence, more memory than presence. Here, ice should rule. The frozen outer planets and dwarf worlds seem, from a distance, like static beads of rock and frost, locked in orbits that change only over ages. Yet as the spacecraft presses farther outward, it begins to find that stillness is an illusion. Under dim light and deep cold, some of the strangest motions in the solar system are quietly unfolding. Neptune and its captured moon Triton receive the first attention. Triton circles its planet in a direction opposite to Neptune's rotation, an orbit that gives away its past. It was likely born elsewhere and seized by gravity, forced into a path that bends against the spin of its new host. Its surface temperature hovers just a few tens of degrees above absolute zero. At such cold, nitrogen and methane become frozen rock. Yet when earlier missions looked at Triton, they did not see a dead sphere. They saw geysers, fountains of dark material rising kilometers into the sparse air and then falling back as fine snow. How can a world so far from the sun have enough internal energy to drive such activity? Why does a captured moon behave more like an engine than an ice cube? The answer begins with tides and with the violence of capture. Triton's unusual orbit suggests that it was once part of a smaller system. When Neptune pulled it in, Triton's path was stretched and reshaped. Over long stretches of time, friction between its interior layers and its changing orbit would have turned gravitational energy into heat. Even now, subtle tidal flexing may continue. The interior stays warm enough, perhaps, for pockets of liquid or at least flexible ice. Heat moves slowly upward. Near the surface, seasonal sunlight can trigger cycles in the thin nitrogen frost. Heating causes gas to build pressure beneath translucent layers. Eventually, that gas breaks through in jets, carrying dust and darker particles with it. The result is a surface marked by streaks and fans, signs that even in the deep cold, the ground is not truly still. The spacecraft does not visit Triton directly on this journey, but its instruments carry the knowledge of that moon forward as a template. When the path bends outward toward Pluto, there is a sense of expectation. If one distant world of ice can move and breathe, what about this dwarf planet at the rim of the known planets? Pluto was once drawn as a small, frozen remnant, a leftover stone at the edge of the map. That image did not survive first contact. As the probe that first flew past Pluto showed, its heart-shaped plane of nitrogen ice is not smooth and ageless. It is divided into giant cells, each hundreds of kilometers across, with raised rims and lower centers. Cracks run along the borders. Dark material collects in troughs. The pattern looks uncannily like the tops of boiling fluid, as seen on a pot of water left on low heat. On Pluto, the timescales are slow, but the behavior appears similar. Warmer ice from below rises in the centers of the cells, spreads, cools, and then sinks along the edges. The surface is the frozen lid of a convecting layer, shifting over spans of millions of years. How can nitrogen ice, which seems so fragile and static, behave like a creeping, overturning sea? The key lies in the delicate balance of temperature, composition, and gravity. Pluto is cold enough for nitrogen to freeze, but not infinitely rigid. Its internal heat, left over from formation and boosted by radioactive decay in its rocky core, can warm the base of thick nitrogen deposits enough to make them flow slowly. Because Pluto's gravity is weak compared to Earth's, even small differences in density and heat can drive motion. The result is a glacier the size of a continent, advancing and retreating, welling and sinking, in cycles that span eras. On the scale of a human life, the surface seems frozen. On the scale of geologic time, it is in motion. At its core, this region of space is a workshop where cold materials are tested against time. Pluto is not alone. Its large moon cairn shows deep canyons and dark northern plains, signs that its interior once expanded and cracked the crust. Lighter and darker patches hint at processes that moved material around after the surface first solidified. Smaller Kuiper Belt objects display varied faces, from the smooth and gently contoured to the heavily cratered and scarred. Some show hints of layering, as if their outer shells have been resurfaced more than once. The message is the same. These are not simply frozen relics. They are records of heat, stress, and change. One of the most striking examples of gentle motion in deep cold is found on Pluto's tenuous atmosphere and its seasonal cycle. As the dwarf planet moves along its elongated orbit, its distance from the Sun changes significantly. When it is closer, a little more light reaches the surface, and some of the nitrogen ice sublimates into gas. The atmosphere thickens. Winds redistribute frost from one region to another. When Pluto moves farther out, the air freezes again and falls as snow. Over time, this cycle can shift the mass of nitrogen deposits across the surface, altering the balance of the crust. Even the changing load of ice can flex the interior, encouraging fractures and possibly driving further convection. A faint atmosphere and thin sunlight still manage to move entire landscapes. Why does this matter beyond the satisfaction of solving a puzzle? It matters because it changes what frozen means. If ice at the edge of our system can flow, crack, and trade places with air, then ice around other stars may do the same. Worlds we once wrote off as inert may, under the right combination of composition and heat, host dynamic surfaces and even subsurface oceans. The boundary between habitable and uninhabitable becomes less sharp when motion and chemistry are considered together. Further outward, in the realm of the smaller Kuiper Belt bodies, the spacecraft's instruments detect faint clues about composition from reflected light. Some objects appear very red, tinted by complex organic molecules built from carbon, nitrogen, and hydrogen. These compounds likely formed when simple ices were bombarded by cosmic rays and ultraviolet light over immense spans of time. The surfaces of these objects are the canvases on which the galaxy has been quietly painting for billions of years. Each impact, each dose of radiation, each slow migration of material across the surface adds another layer to that story. Yet even here, in the most distant reaches, motion refuses to disappear. Binary objects spin around each other in tight dances, as if unwilling to travel alone. Some pairs are so gently bound that a small disturbance could split them forever. Others are in contact, two lobes joined like a snowman, shaped by slow collisions in shared orbits. Their forms preserve evidence of how softly dust and ice once drifted together in the early solar nebula. They are frozen snapshots of formation, but their mutual rotations remind us that even a snapshot can spin. From a human perspective, these motions are almost painfully slow. A glacier on Pluto may take millions of years to shift a few kilometers. A canyon on Charon may widen by centimeters over centuries. A binary Kuiper Belt object may change its rotation only slightly over the age of the dinosaurs. But on the scale of planetary lifetimes, these changes are real and cumulative. A landscape that looks fixed in a single image is, in truth, caught mid-sentence in a story that is still being written. This long view has direct consequences for how we search for life and for how we think about the origin of worlds. If ice-rich bodies can retain internal heat long enough to drive convection, then some of them may also maintain liquid layers beneath their surfaces. We have already seen hints of this closer in, at Europa, Enceladus, and perhaps other moons. In the far outer system, the same principles could apply. An ocean under a thick crust of ice could be warmed by the slow decay of radioactive isotopes, insulated by outer layers, and perhaps stirred by tides if a nearby moon or giant planet provides a rhythm. In such a sea, chemistry could proceed in darkness, fed by minerals from a rocky core. Life on Earth has shown that such conditions can support robust ecosystems near hydrothermal vents. If so, then frozen worlds in motion are not just curiosities. They are potential laboratories for biology under extreme conditions. A thin atmosphere and a mobile surface can transport oxidants and other reactive species from the exterior into cracks and vents. Convection can bring freshly processed material from depth to regions where it can interact with liquid water or other solvents. Radiation that seems destructive at the surface can, in the right quantities and contexts, provide the energy to build complex molecules that later sink into safer zones. The significance extends one step further. The outer regions of a planetary system are also storage spaces for primitive material. Comets and icy bodies from these reservoirs can fall inward, delivering organic compounds and water to inner planets. If the outer system constantly processes and reshapes this material, it might also constantly refresh the supply of chemical ingredients for young worlds. A frozen region at the edge becomes, over time, a quiet supplier of seeds for life closer to the star. As the spacecraft continues its outward journey past Pluto and into the broader Kuiper belt, the sun dims to a bright star and then to a strong point among many. The instruments keep listening. Dust impacts tick against detectors. Subtle changes in charged particles mark the passing of unseen objects and distant currents. The sense grows that the solar system does not end so much as fade into a larger environment. The motions here are not limited to solid bodies and thin atmospheres. They include the slow drift of the solar wind as it stretches and thins, filling the space between these worlds and the boundary beyond which the galaxy's own breath begins to dominate. Ahead, the readings hint at changes that are not driven by ice or rock at all. They are driven by the weakening grip of the sun on the surrounding plasma. The density of the solar wind begins to drop, and the energy of incoming particles from beyond the system starts to rise. The spacecraft is moving toward the place where the frozen motion of worlds gives way to the grander, invisible flow at the edge of the heliosphere, where the wind from our star meets the wider sea of the galaxy. Far beyond the last bright orbits of the giant planets, the spacecraft moves through a realm where sunlight feels more like a direction than a source of heat. The sun behind it is no longer a disk, but a fierce star, brilliant, yet small, with its light spread thin across a dark ocean. Out here, there are no more rings, no more familiar planets, only scattered worlds of ice and rock, and the invisible breath of the star itself. That breath, the solar wind, still flows outward, but it is weaker now. Its particles are more widely spaced, their pressure lower, their grip on space loosening. Somewhere ahead lies the place where that grip fails. For most of human history, the edge of the solar system sounded like a simple idea. Draw a circle around the farthest planet and call that the boundary. Once the first probes began to cross those orbits, it became clear that the real edge is not set by planets at all. It is set by the reach of the sun's wind. The heliosphere is the vast bubble that wind inflates in the surrounding galaxy, a region carved out by charged particles streaming from the solar corona. Inside that bubble, the wind mostly flows outward. Outside it, the particles of the galaxy dominate. The spacecraft is now moving toward the place where one regime gives way to the other. The first sign that it is approaching something new is a change in the wind's character. Instruments that have been measuring a steady outward flow of solar particles begin to see that flow slow. The speed of the wind drops. The density changes. Waves in the plasma shift their pattern. The spacecraft crosses a region where the wind, once supersonic relative to itself, is forced to slow to subsonic speeds as it pushes against the interstellar medium. This is the termination shock, a broad and turbulent boundary where the sun's breath slams into the thin gas between stars and begins to pile up. Crossing the termination shock is not like stepping through a doorway. It is more like entering a storm front. The spacecraft sees increases in energetic particles, the signatures of shocks and compressed fields. The solar wind no longer looks like a straightforward outflow. It appears as a shaken, heated medium, its direction and speed influenced by the pressure of the material beyond. Behind the shock lies the heliosheath, the outer layer of the heliosphere, where slowed solar wind streams and swirls, trying to find a path around the resistance of the galaxy. Inside this sheath, the sun still dominates, but its dominance is contested. The magnetic field lines carried outward by the wind are stretched, twisted, and draped back. The spacecraft measures their orientation and strength, building a picture of how the bubble is shaped. Is it symmetrical? Is it squashed by the flow of the interstellar medium from one side? Does it trail a long wake like a comet? Some models favor a comet-like tail. Others suggest a more rounded, blunt shape, or even something like a warped croissant, with lobes that extend outward in different directions. The data hint at complexity, but they do not yet resolve all doubts. The true shape of the bubble that contains our system remains partly veiled. As the probe moves deeper into the Helios heath, another change appears. Cosmic rays, high-energy particles that come from beyond the solar system, begin to grow more numerous. Inside the heliosphere, the sun's magnetic field and wind deflect many of these particles, shielding the inner planets. Near the edge, that shield weakens. Detectors on the spacecraft register a steady climb in cosmic ray flux, as if the walls of the shelter are thinning. At the same time, the number of low-energy solar particles starts to drop. The balance is shifting from a solar-dominated environment to a galactic one. The most profound transition comes when the spacecraft finally encounters the heliopause, the boundary where the pressure of the solar wind and the pressure of the interstellar medium match. On one side of this frontier, plasma is mostly solar in origin. On the other, it belongs to the galaxy between stars. The crossing is not marked by any visible curtain, yet the instruments record a sharp and enduring change. The density of charged particles from the sun falls dramatically. The density and temperature of the surrounding plasma change to values that match expectations for the local interstellar medium. The direction of the magnetic field bends into a new orientation, aligned more with the galactic field than with the spiral carried by the solar wind. Without any fanfare, the spacecraft has left the sun's immediate domain. At its core, this moment is the biggest reveal of the journey so far. A machine built by a small species on one planet has stepped, by steady motion, from a stellar bubble into the wider ocean of the galaxy. The sun is no longer the sole architect of the space around it. Its wind fades into the background. The environment becomes part of a much older, larger structure, molded by past supernovae, by drifting clouds, by magnetic lines stretched across hundreds of light years. Let this far-off frontier sink in. Like and subscribe to the Quiet Universe channel. The implications of this crossing radiate inward. The heliosphere is not just a shape on a diagram. It is a shield that filters radiation for every world inside it. Its size and structure help decide how many cosmic rays strike our atmosphere, how much energy reaches the outer planets, how stable climate can be over millions of years. If the local interstellar environment changes, the heliosphere's size may change too. A denser region of gas or a different magnetic configuration could compress the bubble, bringing the heliopause closer in, exposing the planets to a harsher flux of high-energy particles. Some researchers propose that passages through such regions over geologic time might influence climate or even biological evolution. Equally important is what the crossing tells us about the galactic neighborhood itself. The interstellar medium near the sun is not empty. It contains gas, dust, and traces of heavier elements, stirred by shocks from past stellar explosions. By sampling this medium directly, the spacecraft becomes an envoy, returning information about the substance into which other stars carve their own bubbles. The density, temperature, and ionization state of this material inform models of how the galaxy recycles matter from old stars into new. Our star's boundary is also an entry point into galactic ecology. The spacecraft continues outward, now traveling through space that no longer belongs primarily to the sun. The flow of plasma around it follows the galactic magnetic field rather than a solar spiral. The cosmic ray background is higher and more stable. The solar wind is now a distant stream flowing out behind, rather than the dominant current. From this vantage, The heliosphere may look like a faint, glowing bubble behind the probe, a region of slightly different conditions embedded in a broader sea. This shift in perspective has a quiet, unsettling power. Inside the heliosphere, the sun feels like the center of the story. Outside, it becomes just one of countless stars with bubbles of influence. The spacecraft is moving through an environment shaped by many distant sources. Shock fronts from ancient supernovae may have passed through here long ago, compressing and heating the gas. The overall direction of the magnetic field may reflect the pull of larger galactic structures. The sun's contribution, while important locally, is secondary in this space. Our home star is still luminous, still massive, still warm to its planets, but it is not a ruler beyond its own carved volume. Why does this matter for us? So far inward, wrapped in our atmosphere and magnetosphere, it matters because it reminds us that our planetary safety net is layered. Earth's field protects the surface from many charged particles. The heliosphere protects that field from much of the galactic flux. The interstellar medium, in turn, shapes the heliosphere. Each layer influences the next. A change in the galactic environment can cascade inward, altering the conditions for life on distant worlds that never see the change directly. The edge of the heliosphere is, in that sense, part of the boundary of our biological comfort zone. There is another, more human meaning in the crossing. For the first time, something we built has become, in a precise physical sense, interstellar. It still orbits the galactic center along with the sun, but it now moves through space where the sun's wind no longer rules. Its trajectory is fixed by a combination of the sun's gravity, the galaxy's pull, and the subtle drag of the medium it crosses. It will never return. It is an arrow that has left the bow, still carrying a whisper of the world that launched it in the form of its metal, its software, and the encoded message attached to its frame. As it drifts deeper into the interstellar medium, the spacecraft experiences a new kind of weather. The density of the surrounding plasma is higher than in the outer heliosphere, though still far thinner than any vacuum chamber on Earth. Waves travel through this medium, driven by fluctuations in the galactic field and by disturbances from distant events. The craft senses these waves as variations in particle flux and magnetic strength. Each fluctuation is a clue to structures that cannot be seen directly, such as large-scale current sheets, boundaries between interstellar clouds, or the lingering signatures of explosions that occurred before humans ever existed. Slowly, a picture emerges of the heliosphere, not as a static bubble, but as a moving object, pushed and sculpted by the medium. On the side where the interstellar flow meets the sun, the boundary compresses. In the trailing wake, it stretches. Depending on the orientation of the galactic magnetic field, the entire structure may be tilted or twisted. Our system is, in effect, sailing through the galaxy with its protective shell shaped by the cosmic winds it encounters. The spacecraft, sampling conditions in the wake of the crossing, helps reveal how smooth or rough that journey really is. This knowledge feeds back into our understanding of other stars. Each star with an outflow of charged particles likely has its own heliosphere-like bubble. Those bubbles interact, merge, and overlap in regions where stars are crowded. In some cases, they may protect planets from external radiation. In others, they may channel particles in ways that increase exposure. The balance of stellar wind pressure and interstellar conditions could help determine which planetary systems are more stable havens for life. The crossing of our own boundary thus acts as a small test of a much larger pattern. The farther the spacecraft travels, the fainter the sun's influence becomes in its data. Yet the memory of that influence remains encoded in the changing composition of particles it saw on the way out. Scientists can trace how the energy spectrum of cosmic rays shifted as the probe neared and then left the heliosphere. They can compare measurements inside and outside the bubble to test models of how effectively the heliosphere shields inner space. Those comparisons will refine estimates of radiation environments for future deep space missions and for any long-term presence humans might someday establish around other planets. Eventually, the probe will fall silent. Its power source will fade, its instruments will cool, its radio voice will stop. Long after that, the spacecraft will continue forward as an inert relic, a small artifact moving through a medium it can no longer describe. The heliosphere behind it will continue to flex and breathe as the sun ages and as the galaxy changes. Other interstellar scouts may follow, carrying more sensitive instruments, mapping the boundary in more detail, perhaps even exploring other directions where the heliosphere's shape is different. Even then, this first crossing will retain a special significance. It turned a line on a theoretical diagram into a place we have touched with instruments and patience. It turned the idea of a stellar boundary into a measured transition with numbers, profiles, and uncertainties that can be refined. Above all, it showed that the seeming emptiness between stars has structure, pressure, and history. The path ahead from this edge leads into that structure, into the darker lanes between clouds where atoms combine into more complex forms, and where the faint molecular seeds that may one day rain down onto planets drift in the long night between suns. Beyond the sun's fading wind, the spacecraft moves through a darkness that is not empty. The stars ahead look sharper, their light no longer softened by the dust and plasma of the heliosphere. Between those stars lies a medium so thin that a cubic centimeter might hold only a few atoms, yet stretched over light years. That scarcity becomes substance. Here and there, the density rises. Gas and dust gather into clouds, some faint and wispy, others so thick that they blot out the starlight behind them. To the eye, these dark patches seem like absences in the sky. To a careful instrument, they are the opposite. They are reservoirs of matter, places where the galaxy stores its raw ingredients. The spacecraft cannot see these clouds in visible light. They appear only as missing stars. But its sensors can pick up other clues, whispers in radio waves and infrared emissions. Longer before any craft reached this region, telescopes on and around Earth found that these clouds carry distinctive signatures. Certain wavelengths appear more strongly, emitted by molecules rotating and vibrating in the cold. Each pattern of lines is a fingerprint, a sign that a particular molecule is present. Simple ones appear first: hydrogen molecules, carbon monoxide, ammonia, then more complex forms show themselves: methanol, formic acid, chains of carbon and hydrogen. The dark is chemically alive. At first glance, this seems backward. These clouds are cold, often only a few tens of degrees above absolute zero. They are shielded from bright starlight by their own dust. That shielding keeps them cold, but also blocks many energetic photons that might drive reactions. How can chemistry flourish here? How can complexity arise in a place where nothing much seems to happen? The answer lies in a different kind of energy and in the surfaces of tiny grains of dust drifting through the gas. Each grain is a speck of mineral or carbon, perhaps a fraction of a micrometer across. On its surface, atoms and simple molecules can stick for a time. Hydrogen, oxygen, carbon-bearing species land and stay. In the extreme cold, they migrate slowly across the grain, and occasionally two meet. When they do, they can react, forming new molecules that would be hard to build in the gas phase alone. Thin films of ice form around these grains, made of water, carbon monoxide, carbon dioxide, methane, and other simple compounds. Cosmic rays, those high-energy particles that roam the galaxy, pass through the clouds and strike these ices. Their energy breaks bonds and rearranges atoms. With each impact, the mixture becomes a bit more complex. At its core, this is chemistry driven by patience. Reactions that would be rapid in a warm lab take thousands or millions of years here. But the cloud has the time to spare. Layers of processed ice eventually get disturbed. Shocks from passing waves, encounters with other clouds, or the gentle pull of gravity as parts of the cloud begin to collapse, can heat the grains or knock surface molecules back into the gas. When that happens, the complex species that have been assembled on the grains become part of the larger environment. The spectral fingerprints we see are a direct result. The list of detected molecules has grown with every improvement in our instruments. Alcohols, nitriles, aldehydes, and other organics have been found in these cold regions. Some are direct precursors to amino acids and sugars. None of them are life. They are not cells, not even self-replicating systems. Yet they show that the galaxy is chemically busy. It does not wait for planets to appear before starting to assemble interesting structures. It uses dust grains as scaffolds and cosmic rays as chisels, sculpting molecular seeds in the dark. Why does that matter? Because it changes how we think about the origin of life's building blocks. If complex organic molecules can form in interstellar clouds long before planets exist, then the ingredients for life do not need to be manufactured entirely on worlds like Earth. They can be inherited. When a portion of a molecular cloud collapses to form a star and its surrounding disk, it brings with it a cargo of pre-assembled compounds. Those compounds can freeze into comets, accrete into planetesimals, and rain down onto young planets as impacts. The chemistry of the cloud becomes the chemistry of oceans and atmospheres later on. The spacecraft gliding through the local interstellar medium does not have a full lab on board, but it can still sample certain aspects of this process. Dust detectors can measure impacts from grains, estimate their sizes, and hint at their composition through the way they break apart. Particle instruments can detect neutral atoms and ions drifting in from denser regions, their energies and directions shaped by large-scale flows. Combined with observations from distant telescopes that peer into more massive clouds than the one we inhabit, these data build a picture of a galaxy in which dark patches of sky are, in fact, factories. There is a quiet tension here. On Earth, we often associate darkness with emptiness. A starless patch of sky looks like nothing at first glance. Yet some of the richest chemistry we know happens in those very places. A cloud that hides light can protect fragile molecules from being destroyed by harsh radiation. It can create a safe, cold cradle where slow reactions can proceed. Is it possible that, in cosmic terms, darkness is sometimes more fertile than light? What does it mean if the seeds of biology are most efficiently assembled in places where no eye can see? The idea that organic molecules drift through space is not new. Meteorites that have fallen to Earth carry amino acids and other complex species that formed in their parent bodies or in the clouds from which those bodies were born. Comets have been found to carry organics as well, their comas and tails showing off the chemicals released as ices evaporate. These findings blur the line between interstellar chemistry and planetary chemistry. The same molecules that appear as faint spectral lines in a dark cloud can later become part of the crust, oceans, and air of a young world. Think about what that implies for other systems. Wherever a star forms within a molecular cloud, it inherits this chemical legacy. Disks around young stars are bathed in gas rich in water, carbon-based molecules, and nitrogen-bearing compounds. Planets that grow from those disks start with more than just bare rock and ice. They are born into an environment already primed for complexity. If that is true, then the galaxy may be seeded, over and over, with worlds that never begin from a blank chemical slate. There is room for uncertainty in how far this process can go before life itself emerges. Some models suggest that interstellar chemistry can produce molecules as complex as simple sugars and basic amphiphilies, which can form membrane-like structures. Others are more cautious, pointing out that the step from complex organics to self-replicating systems is still immense. Yet there is a growing sense that the gap between non-living and living chemistry may not be as lonely as once thought. The road to life may start in the cold mist between stars, long before the first sunrise on any planet. From the spacecraft's perspective, this is more than an abstract realization. It is passing through the outskirts of the same kind of environment that once collapsed to make the Sun and its family of planets. The local interstellar cloud through which we travel is not a massive star-forming complex, but it still bears the marks of past events. The density of atoms, the ratio of different elements, the strength and orientation of magnetic fields, all hint at a history of shock waves and enrichment from older generations of stars. Supernovae spread heavy elements into space. Red giants shed carbon-rich layers, All of that material becomes part of the clouds where new systems are born. Why does this long chain of events matter to beings on a small rocky planet? It matters because our own bodies are built from atoms, forged in those earlier stars and molecules shaped in those ancient clouds. The carbon in our cells, the nitrogen in our DNA, the oxygen we breathe, were all once part of diffuse gas between suns. The dark patches that now hide stars from view are, in a real sense, our ancestral neighborhoods. Knowing how they work is a way of understanding where we come from on a scale larger than any single world. As the mission continues, attention turns to how these molecular seeds might be sampled more directly in the future. Current instruments can only infer the presence of many species through remote sensing. To truly understand the range of molecules and their distributions within a cloud, we would need to send probes capable of flying through denser regions, taking in situ measurements, and perhaps even returning material. That thought begins to shape the next step in our journey. If we want to track the path of these seeds from cloud to planet, we will need machines that can survive for centuries, navigate far from the sun, and function in environments where power from starlight is almost non-existent. Even now, the spacecraft feels the first constraints of this challenge. Its power source weakens with time. Its antenna must maintain alignment with a distant point of light that grows dimmer by perspective. Even if its true brightness has not changed, communication delays stretch, turning every exchange into a conversation with echoes. The idea of sending probes even farther, into thicker parts of molecular clouds or the space between them, forces us to rethink how we build and operate our tools. Some proposals imagine fleets of tiny craft accelerated to high speeds, skimming through interstellar gas and dust while sampling their surroundings. Others envision larger, slower probes that carry their own long-lived power sources and autonomous laboratories. All share one requirement: they must operate largely alone, making decisions without constant guidance, reading subtle signals from the dark and turning them into understanding. The story of molecular seeds in the dark is therefore not only about chemistry, it is also about the limits of our reach and about what kind of machines we will need if we want to map the galaxy's quiet factories firsthand. Ahead, the narrative begins to shift from what the universe has already made to what we might build to explore it, toward a chapter where probes themselves become the next step in our species' long conversation with the spaces between stars. The first machines that slipped past the outer planets did not intend to become interstellar travelers. They were built to glance at Jupiter, Saturn, Uranus, Neptune, and then send back photographs before their power faded and their voices thinned into noise. Yet their paths were set by celestial mechanics, and those paths did not end at the orbits of planets. They bent outward, away from the sun, into the long dark between the stars. Decades later, those machines are still moving, long past the last worlds they were meant to visit. Their instruments dim, but their momentum unchanged. They have become witnesses, where no human will stand for ages. They are the first hint of a coming era in which machines, not bodies, will be our presence on the interstellar frontier. The story they tell is as much about limits as it is about achievement. Chemical rockets carried them away from Earth with great force, but their final speeds are small compared to the scale of the galaxy. At tens of kilometers per second, it will take tens of thousands of years just to travel a single light year. Their power sources, based on the slow decay of radioactive elements, fade on timescales of decades, not millennia. Their transmitters were tuned to talk to a planet, not to speak across centuries. They are heroic, but they are also temporary. If we want to explore the spaces between stars deliberately rather than accidentally, we will need machines built for distances and durations that dwarf anything we have attempted so far. This need creates a deep tension. The galaxy is large, cold, and slow in its motions, while our lives are short and our patience limited. How do you design an expedition that may take longer than the lifespan of a civilization? How do you build a probe that must think for itself in situations its makers could not foresee? How do you maintain a thread of communication across distances where a single message can take years to arrive and years to return? Are we prepared to send machines into a journey that may never report back in time to answer the questions of those who launched them? One family of ideas tries to sidestep the problem of duration by attacking the problem of speed, instead of pushing heavy craft with chemical rockets and letting them drift. We can imagine using light itself as a source of momentum. A sail made of thin, reflective material can capture the tiny push of photons and, over time, build up to impressive speeds, closer to a star. Sunlight alone might be enough to drive such a sail outward. Farther out, powerful directed beams from large arrays could take over, pushing small probes to fractions of the speed of light. A gram-scale craft attached to a thin sail, hit by a sustained, coherent beam, might cross the gap to nearby stars in decades instead of millennia. Yet this path comes with its own challenges. A craft that small has very little room for shielding or complex instruments. It must survive impacts with dust and stray atoms at enormous speeds. Its sail must remain intact under intense radiation and pressure. The beam that accelerates it must be aimed with extraordinary precision, or the craft will drift off course. And once it reaches its target, it must gather useful data and send it home with only a tiny power source. Fast travel demands extreme simplicity and extreme robustness. The dream of reaching other stars quickly becomes a problem in miniaturization and endurance. Another family of concepts accepts slower travel but focuses on resilience. Large, comparatively heavy probes can carry more instruments, thicker shields, and robust power sources. They might rely on advanced nuclear reactors or on long-lived radioisotopes. Their trajectories would be carefully planned to take advantage of gravitational assists, turning the mass of planets and stars into subtle boosts. These craft would not reach their destinations in a human lifetime, but they would be built to outlast generations. Their mission design would assume that the people who receive their final reports are not the ones who launched them. In both cases, speed and resilience converge on a common requirement. The machines must be able to function with a high degree of autonomy. The farther they travel, the less frequent and less timely our instructions become. Deep in interstellar space, a probe cannot wait for permission to act when a system fails or an opportunity appears. It must detect the issue, test a response, and decide on a course of action on its own. That autonomy must be careful and constrained, yet flexible enough to handle surprises. In a sense, each craft becomes a small, self-contained decision-maker, guided by priorities encoded at launch but faced with situations that no planner could fully predict. The core of such a machine is not its engine or its antenna, but its ability to turn environment into information. This is the single metaphor that defines its nature. It is a signal engine. It moves not simply to occupy new locations, but to transform unknown conditions into patterns that can be sent back across the void. Fields become voltages. Photons become bit streams. Impacts become data points. The value of the probe lies in how well it can collect, compress, and transmit these signals over distances where every bit is precious and every watt of power must be justified. To navigate such journeys, future probes may rely on the universe itself as a map. Pulsars, rapidly spinning neutron stars that emit beams of radiation from their magnetic poles, can act as natural beacons. Their pulses arrive with remarkable regularity. By comparing the arrival times of pulses from multiple pulsars, a probe can triangulate its position in three-dimensional space much as sailors once used the stars. Onboard clocks and detectors can build a local coordinate system tied not to Earth, but to the galaxy. Navigation then becomes less dependent on constant contact with home and more dependent on the probe's ability to read the sky. Star trackers, inertial sensors, and measurements of the local interstellar medium add further information. The pattern of the galactic magnetic field, sampled over time, can serve as a reference. Density gradients in the surrounding gas can signal the approach of clouds or boundaries. Each new measurement is another anchor point in a frame of reference that is not tied to any planet. The probe becomes both traveler and cartographer, building a map as it moves. Communication remains the most unforgiving constraint. Radio waves, even at their most focused, spread and weaken over interstellar distances. A transmitter with the power of a light bulb, pointed at a distant receiver, can be lost in the noise of the universe unless extraordinary care is taken. Laser communication, with its narrower beams and higher frequencies, promises better efficiency, but it also demands finer pointing and more precise alignment. A small misdirection can mean missing the Earth entirely. For probes that travel for centuries, the positions of both sender and receiver will have shifted significantly, following gravitational paths around the galactic center. One way to ease this difficulty is to imagine a network rather than a single link. Instead of one lonely machine broadcasting across many light years, we can think of multiple probes forming a thin chain, each relaying signals to the next. Some might linger near the boundary of the heliosphere, others near intermediate distances, others near target stars. As each receives data from its outward neighbor, it amplifies and forwards the information inward. Such a network would be fragile, vulnerable to the loss of individual nodes, but it would also be more flexible. It could be extended, repaired, and adapted over time, like an expanding nervous system reaching out into the galaxy. The design of machines for this frontier must account not only for physics, but for time. Metals corrode, lubricants degrade, circuits suffer from radiation damage. Even the most robust electronics can fail when particles pass through them, flipping bits or burning out components. One response is redundancy. Critical systems can be duplicated, triplicated, or more, so that failures can be tolerated. Another response is self-monitoring and, in limited ways, self-repair. Probes might carry spare memory modules, reconfigurable logic, or robotic arms capable of swapping out components in predefined ways. They will not be fully self-healing, but they might be able to compensate for the most likely kinds of damage. There is also the question of heritage and evolution. The first generation of interstellar-capable probes will teach us where our expectations were wrong. They will fail in ways we did not anticipate. The second generation will incorporate those lessons, improving designs, adjusting strategies. Over many cycles, the machines we send may begin to diverge much as species diverge, each new design optimized for a particular kind of mission or environment. Some might specialize in mapping the structure of the interstellar medium. Others might focus on flying through dense clouds to sample their chemistry directly. Others might be built to orbit distant stars and listen for signals from their planets. Why does this matter for us here and now? Sitting on a world that has not yet sent even a single craft to another star, we live at the beginning of this process. The choices we make about how to build, launch, and interpret the first wave of deep probes will shape the story for centuries. The architectures we test, the philosophies we embed in their autonomy, the kinds of measurements we prioritize. All of these will echo outward, in a very real way. The first interstellar machines are also the first long-term policies we impose on our future presence in the galaxy. The scientific payoff is immense. Machines that travel beyond the heliosphere can sample the local interstellar medium directly, refine our understanding of how stars interact with their surroundings, and test theories about the structure of the galaxy's magnetic field. Probes that reach other systems, even with flyby missions, can observe planets and debris disks from vantage points impossible to achieve with telescopes alone. They can look back at our own sun from afar, comparing it to its neighbors. They can map how molecular clouds feed material into forming stars on scales larger than any single system. There is also a cultural and existential payoff that is harder to quantify but no less real. Sending machines into the interstellar frontier is an assertion that we intend to be more than passive occupants of a small world. It is a statement that we are willing to invest in projects whose completion lies far beyond personal or even national lifetimes. It raises unsettling questions as well. Who speaks for a mission that will outlast those who funded it? Who bears responsibility for decisions that may play out long after our languages and institutions have changed? Do we owe anything to the machines themselves? These long-lived emissaries that will spend their existence in isolation, translating silence into data. Speculation about more advanced possibilities arises naturally. Some dream of self-replicating probes that harvest material from asteroids or interstellar dust to build copies of themselves, spreading through the galaxy in an exponential wave. Others imagine world ships, carrying not just instruments but ecosystems and people, moving at slower speeds but in far larger, self-contained habitats. The ethical and practical questions around such ideas are deep. A self-replicating system must be constrained to avoid consuming more than it should. A world ship raises issues of governance, identity, and continuity across generations. For now, these remain concepts sketched on paper and in stories, but they serve as boundary markers for what might one day become technically possible. In the nearer term, the machines that define the interstellar frontier will probably be small, focused, and patient. They will map, detect, test, and measure. They will follow signals rather than blaze obvious trails. They will spend most of their existence in darkness, with only occasional flares of information flowing through their circuits. They will be, in many ways, more persistent than the cultures that launched them. Long after buildings crumble and borders shift, these probes will still be moving, still carrying their encoded questions outward. As we imagine them, it is easy to slip into thinking of them as replacements for us. Yet they are not. They are extensions. They do not remove the human element of exploration. They stretch it. The data they return will be interpreted by minds that did not witness the launch, by scientists who may think in ways we cannot predict. In that sense, the machines are bridges not only across space, but across time. They tie our present curiosity to future understanding through a continuous thread of measurement. Eventually, some of these machines will move so far that the sun becomes just one star among many in their field of view, indistinguishable without careful analysis. They will drift past clouds where new stars are forming, past streams of molecular seeds, past the quiet pulses of distant pulsars. From their vantage, the idea of a single home system will blur. They will see patterns on larger scales, gradients across kiloparsecs, the way clusters of stars feed and drain the interstellar medium. Their recordings will show us our place, not just in a solar system, but in a galaxy. The journey of these machines sets the stage for a final turn in the story, a shift from engineering and measurement to meaning. When we send devices to roam a galaxy that will outlive us, we are not just asking what the universe is made of, we are also asking what it means for a small, self-aware species to leave its traces in a cosmos this large, and what kind of story continues when our instruments travel on without us. The spacecraft drifts onward through a region where the difference between motion and stillness becomes difficult to name. The sun lies far behind, a bright point among countless others, its warmth too faint to shape the environment in any clear way. Ahead stretches the wider galaxy, a landscape made not of surfaces, but of distances and invisible currents. In this expanse, scale overwhelms familiar meaning. A grain of dust can drift for millions of years before colliding with another. A cloud can take tens of millions to collapse into stars. Time itself feels stretched, as if the pace of the universe slows the farther one travels from the heat of a star. In this quiet, the mission becomes less about measurement and more about perspective. Every earlier chapter of the journey revealed a layer of structure, the confusion of the solar wind, the storming kingdom of Jupiter, the fragile balance of Saturn's rings, the slow choreography of Pluto and other distant bodies, the thinning wind at the heliopause, the chemistry of the dark clouds, and the machines that must interpret it all. Out here, these layers stack like memories. They no longer appear as separate puzzles. They merge into a single arc, a long unfolding of how the sun communicates with the galaxy, how the galaxy shapes the sun, and how small instruments carry those messages across the boundaries between them. The spacecraft itself is an emblem of that arc. It is built from metals forged in ancient stars, assembled on a world illuminated by one star, launched by a civilization whose own lifespan is brief, and now traveling through space molded by stars that died long before that civilization existed. A quiet symmetry emerges. The machine is a product of stellar history, sent to read the history written in the material between stars. Nothing about it is out of place. Even its solitude feels natural, as though interstellar space is less a void and more a library where every grain and particle carries a page of ancient text. The deeper the craft moves, the more the galaxy reveals its dual nature. On one hand, it is a place of extremes, shaped by explosions that scatter heavy elements into the medium and by collisions of entire clouds. On the other hand, it is a place of gentleness, where molecules assemble atom by atom on grains of dust and drift for ages before being folded into the birth of stars. Violence and subtlety coexist at every scale. A dying star can seed a region with the material needed for life. A shockwave can sculpt a cloud into a cradle for new worlds. A darkness so deep that it hides starlight can also host chemistry essential for biology. The spacecraft senses this duality in each fluctuation it records. A rise in cosmic rays tells of distant events that still echo across the galaxy. A shift in the magnetic field hints at currents flowing through clouds light years wide. Every measurement is both immediate and ancient. The data points belong to the present, but the forces behind them come from epochs long before the sun formed. To study the galaxy is to study time on scales that do not align with any human rhythm. This mismatch forces a kind of humility. On Earth, we often treat our brief span of centuries and millennia as the natural tempo of progress. Out here, that tempo collapses. A single orbit of the sun around the galactic center lasts hundreds of millions of years. The transit of a molecular cloud past our system might take longer than all of recorded human history. Our timelines shrink until they become thin threads woven into a much larger tapestry. And yet, the spacecraft proves that scale alone does not define meaning. Even a fleeting moment can carry the weight of discovery. When the craft crossed the heliopause, it turned a theoretical boundary into a known frontier. When it sampled the changing density of the interstellar medium, it traced a curve through space that no earlier instrument had drawn. These small acts show that understanding does not depend on matching the universe's timescale. It depends on being present, attentive, and willing to follow the signals wherever they lead. At its core, the journey reflects a quiet truth. The universe is not arranged for our convenience, yet it is legible. Its structures do not need our presence, yet they can be read. We are late arrivals to a galaxy that has been evolving for billions of years, but late arrivals can still listen, still learn, still send fragile machines across unimaginable distances to gather stories written in dust and plasma. Meaning comes not from how central we are, but from how deeply we choose to observe. As the probe continues, its power diminishes. Eventually, its voice will fade until no antenna can hear it. But fading is not erasure. Every bit of data it sent has already shaped models, theories, and expectations. The machine may grow silent, but its contributions are now part of the long conversation between humanity and the cosmos. Its silence will mark not an end but a transition, a reminder that the work of interpreting the universe continues even when individual instruments fall quiet. In one sense, the spacecraft is alone. There are no planets nearby, no lights, no other machines. But in another sense, it drifts inside a vast community of stars, clouds, and fields that share material through explosions and gentle flows. The atoms that make up the craft will one day be scattered too, swept into the interstellar medium when the sun eventually expands and sheds its outer layers. In the far future, those atoms might contribute to a new cloud, perhaps to new stars, perhaps to worlds that will wonder about the ancestors that moved before them. A line from an old reflection captures the spirit of this moment. We are made of the same elements as the stars, arranged into shapes capable of asking how those stars came to be. The quote does not need a name. Its power lies in the idea itself, simple and steady. We are matter that has learned to question matter. The spacecraft's path is now a line pointing toward regions where clouds grow denser and the seeds of future systems drift in quiet formation. Those seeds will one day collapse, ignite, and build new worlds with their own brief histories and their own watchers. The cycle will continue long after our small craft has become dust. In that thought lies the final echo. The universe is vast enough that meaning does not have to be universal to matter. A species can find value in sending a signal into the dark, even if the dark does not answer. A machine can cross the boundary between star and galaxy, even if no one lives long enough to greet its final transmission. As the craft moves forward, the map ahead grows dim and the questions grow larger, leaving us with one that may outlast every mission we send. If machines can wander where we cannot, how far into the galaxy can our curiosity travel before the questions become greater than the answers we are able to receive?